For three-dimensional geometries, how to set up the SRF problem or geometry. For three-dimensional geometries, we can define the particular geometry using an axis of rotation. So in this case, this is the axis of rotation. Preferably, we can keep it as any Cartesian axis, although it is not mandatory. We need to define both the rotational axis origin and the direction for the fluid domain. Rotationally periodic boundaries are applicable if geometry and flow is periodic, so we can consider only a section which is periodic along the rotation. Using rotationally periodic boundaries, we can use smaller computational domain instead of actually considering the entire domain. So we consider only part of the domain. Now, after setup and selection of geometry, the next step that we need to do is to select the solver type. For this, we go to the general settings dialog box. There are two choices: pressure based solver and density based solver. The pressure based solver is recommended for incompressible flows and low speed compressible flows. Examples of such problems are CFD of fans, blowers and pumps. The density based solver is the other option. It is recommended for high speed compressible flows. Examples of such problems are high pressure axial compressors, turbines and turbochargers. The solver selection is sometimes also dictated by the physics model. So in case where we want to model combustion and multi-phase flow, we have to go with the pressure based solver. It is recommended that you use the velocity formulation that will result in most of the flow domain having the smallest velocities in the frame, thereby reducing the numerical diffusion in the solution and leading to more accurate solution. So the absolute velocity formulation or the relative velocity formulation is selected here in this particular general settings tab. The absolute velocity formulation is preferred in applications where the flow in most of the domain is not moving. Example, a fan in large room. The relative velocity formulation is appropriate when most of the fluid in the domain is moving. Examples are large impeller in a mixing tank. Now it is recommended that you use the velocity formulation that will result in most of the flow domain having the smallest velocities in the frame, thereby reducing the numerical diffusion in the solution and also leading to a more accurate solution. The absolute velocity formulation is preferred in applications where the flow in most of the domain is not moving. An example can be fan in the large room, whereas the relative velocity formulation is appropriate when most of the fluid in the domain is moving, as in case of large impeller in a mixing tank. So the next setting that we are going to see is the velocity formulation selection. We have seen in the earlier slides that we have two types of ways in which we write the momentum equation in case of moving reference frame modeling. There is a relative velocity formulation and the absolute velocity formulation. So let us see what are the different criteria for selecting the velocity formulation. We can use the absolute velocity formulation when the inflow comes from the stationary domain. Also, cases where we know absolute total pressure, total temperature or absolute velocities, we can use the absolute velocity formulation. For relative velocity formulation, we use this when we have closed domains or if all surfaces are moving or if inflow comes from a rotating domain. Also, if we know relative total pressure, relative total temperature or relative velocity, we can use this formulation. But it should be noted that the relative velocity formulation and the absolute velocity formulation are equivalent and therefore either can be used successfully for almost any problems. Difference between solutions should disappear with suitable mesh requirement.